Welcome to AI Paper Slop, the series for AI researchers, ML engineers, and, basically anyone building the future of autonomous systems. We are jumping right into it today.
Let's do it.
So the paper is called ST-WAM, Semantic-Temporal World Action Model for Robust Manipulation Under Visual Distribution Shifts. It's authored by a team from Tsinghua University, Alibaba Group, and a few others.
It's a big one.
Huge. So here is your 30 to 60-second summary to just get us grounded. Current world action models, or WAMs, rely really heavily on predicting future video frames, right? They use pixel generative supervision. But when the visual environment shifts, like say the lighting changes or the background is different, these models hallucinate their training data instead of dealing with the actual physical space they're in.
Right, they just regress.
Exactly.
Okay.
So ST-WAM fixes this by using DINO semantic features for both predicting the future and retrieving task history. And this dual approach boosts zero-shot robustness on the LIBERO-Plus benchmark by over 21%. Plus, it more than doubles real-world success rates under visual shifts. And it does all this without needing massive embodied pre-training.
Which is, that's just a massive conceptual leap for the whole field of robotics. We spent, the last few years totally obsessed with getting models to perfectly imagine the literal pixels of the future.
Yeah, pixel-perfect prediction.
Right. But this paper proves that you can and absolutely should completely decouple action-relevant state transitions from task-irrelevant visual noise. If you're an ML engineer training policies for real-world deployment, this changes how you should think about future representations entirely.
Yeah.
It proves a robot just needs to understand the structural meaning of a scene rather than getting bogged down by the RGB values of, every single pixel.
So let's unpack that core failure mode first, because, hallucinating training data is a fascinating phrase, but we need to see what that actually looks like.
Oh, it's wild when you look at the data.
Yeah, so looking at the baseline models, things like Fast-WAM and Wan-VAE, on the standard LIBERO benchmark, they are incredible, like success rates of 97.6% and 98.5%.
Basically flawless.
Basically flawless. But then you have LIBERO-Plus, which introduces these visual distribution shifts. They swap out background textures, change the lighting, move the camera viewpoints. And when you evaluate those exact same state-of-the-art models, zero shot on LIBERO-Plus, performance just tanks. Fast-WAM plummets to 51.5%.
At the cliff. It just falls off a cliff.
Right. So the researchers actually did a manual audit. They didn't just look at the aggregate numbers. They sampled 180 individual predictions under these shifts, and a staggering 70.6% of them showed what they coined training-distribution hallucination.
Yeah. And when you look at the latent space representations during those failures, you see exactly what they mean. Because when the current observation deviates from that really tight distribution the model saw during training, the predicted future video actually drifts backward.
Like it's regressing.
Exactly. It starts generating futures that look like the training domain rather than staying faithful to the visually shifted scene it's actually looking at right now.
Wow.
And it happens because of that pixel generative supervision we mentioned. When a model is penalized mathematically for not generating the exact pixels of the future, it sort of panics when the starting pixels look unfamiliar.
So to minimize its loss.
It falls back on the visual statistics it memorized. It essentially entangles the what to do, the action with the what it should look like, the pixels.
It's like, think of an autonomous driving model trained only in sunny California. Suddenly you drop that system into a whiteout snowstorm in Michigan.
Oh yeah, perfect analogy.
Right. And instead of processing the snow, its internal world model just starts hallucinating palm trees and dry pavement. It literally forces the only reality it knows over the complex reality it's actually experiencing.
And obviously that leads to a crash.
Obviously.
Yeah.
So if forcing the model to generate exact pixels is the disease, the cure has to be changing how the model sees the future. But they had to empirically prove that, right? So they ran this controlled representation diagnosis to compare Wan-VAE latents against DINO v3 features.
And this diagnosis setup is just incredibly elegant. They pulled 290 frame triplets from the LIBERO datasets. In each triplet, you start with 2 initial frames. They capture the exact same task state, meaning, the robot's joint positions are identical, the object placements are mathematically the same, but they're captured under completely different visual conditions.
So one is like a clean frame from training, and the other has weird lighting or a different background.
Right. Then they add a third frame to the triplet. This final frame is from the same demonstration, but it represents a totally different point in time, a different state.
Okay, so to visualize this, you have state A in perfect lighting, state A in shifted lighting, and then state B a different pose back in perfect lighting.
Exactly. And the numbers they got from this are just, they're crazy. When they analyzed the DINO v3 features, the average cosine similarity between the two same-state frames was 0.904.
That's super high.
Yeah, but for the Wan-VAE latents, that similarity dropped to 0.686.
Wow.
And it gets worse for VAEs when you actually ask the representations to match the frames. DINO v3 paired the visually shifted frame to the clean same-state frame 95.2% of the time. It understood that despite the shadows, the physical reality was the same.
And the
The
VAE...
VAE latents only made that connection 60.0% of the time.
Wait, really? 60%?
Yeah. So in 40% of the cases, the VAE thought the visually shifted frame was more similar to the completely different task state, just because the pixel statistics confused it.
I mean, that makes perfect sense when you think about what DINO v3 actually is. It's this massive, self-supervised visual encoder. It's trained to understand the structural, semantic properties of images. It tracks the meaning of the scene. A mug is a mug, in the dark or in the light.
Right, whereas VAEs are optimized for visual reconstruction. Their entire job is to care about pixels. So when the pixels change, the VAE latent representation warps drastically.
And it takes the model's physical understanding down with it.
Exactly. But here's where the ST-WAM architecture gets really clever. They prove DINO v3 is vastly superior for state stability. But they don't just throw the VAEs out entirely. They propose what they call dual-space future experts, or DSFE.
Okay, so how does that work?
Think of it like a movie director and a choreographer. DINO is the director. It focuses on the macro semantics like the actor needs to move to the couch. That's your structural stability. The VAE is the choreographer, focusing on the microdynamics. How exactly do the feet step, shift weight, that sort of thing.
Ah, okay.
Yeah.
Because VAEs are still good at capturing those fine-grained visual dynamics from video pre-training.
Right. High-frequency motion details. So ST-WAM runs both features at once. It jointly models feature states in both spaces.
Jointly. That sounds computationally heavy. How are they structurally mapping that out?
So they use the Wan 2.25b video DIT, the diffusion transformer, to model the VA latent space. And in parallel, they use a semantic future DIT to model the DINO feature space.
Like it.
And they bring both of these, alongside an action expert, into a three-branch mixture of transformers architecture. And they train the whole thing using flow matching.
Right. And for anyone listening who might be less familiar, flow matching basically creates a more direct, efficient mathematical path to map complex data distributions, instead of the standard diffusion process of just iteratively adding and removing noise.
Yeah, it's much more stable for this kind of joint modeling.
So we have this three-branch mixture of transformers: visual branch, semantic branch, action branch. But for them to work together, they have to communicate. The paper mentions a structured cross-branch attention mask. And reading through, that mask seemed to be the linchpin of the whole training setup.
Oh, absolutely. The mask is arguably the most critical engineering decision they made. It strictly controls which tokens are allowed to attend to which other tokens.
Break that down for us.
Sure. So first you have the clean current observation tokens, both the VAE and DINO representations of what the robot sees right now. These act as the anchors. They can interact with each other, but they are completely blind to the future.
Makes sense.
Then you have the noisy future streams being generated. The mask allows these future visual and semantic streams to attend to each other, so the DINO semantics can guide the VAE visual dynamics and vice versa. And crucially, those future streams can look back at the current anchors to ground themselves.
But then what about the action tokens, the ones actually outputting motor commands to the robot arm?
Right. The mask puts a massive restriction on them. They can attend to the current observation streams, but they are strictly, completely blocked from accessing any of the future streams.
Okay, so if I'm an ML engineer listening to this, right, trying to deploy real-world robotics, a massive red flag is going up.
Latency.
Yes, latency. If we are predicting two different massive future spaces through a mixture of transformers, inference is going to be incredibly slow. If a policy takes 2 seconds to generate an action, the robot is practically useless.
Yeah, that latency bottleneck is exactly what you'd assume. But this is where the brilliance of that masking strategy really pays off. Let's look at the causality.
Okay.
During training, the action tokens have to learn to predict motor movements without peeking at the future streams. If they could see the future, they'd just cheat and copy the answer.
Right, target leakage.
Exactly. Because they are masked, the network is forced to bake all the necessary predictive power into the representations of the current state. The future streams are merely there during training as an auxiliary objective. They force the underlying current representations to become super robust.
Oh, wow.
So by the time you finish training, the action branch has already learned how to extract everything it needs from the present.
Wait, so you don't even need the future branches at inference time?
You literally snip them off entirely.
That is brilliant.
Right. At deployment, ST-WAM operates purely as an action-only policy. The future prediction heads are completely dropped. On a single NVIDIA A100 GPU, generating a 32-step action chunk takes just 756.17 milliseconds.
Just under a second. So you take a massive computational hit during training to run the dual future generation, and you buy yourself a lightweight sub-second policy at deployment.
Exactly. It's only a 1.24x latency overhead compared to the baseline Fast-WAM, but you get all the robustness of semantic-temporal modeling.
That completely flips how we usually think about scaling inference in world models. But let's pivot a bit, because fixing how the model looks forward is only half the battle.
Right, the perspective fix.
Yeah. What if a heavy shadow falls across the drawer you're trying to open right now? Your current observation is visually corrupted. Does the model just guess based on that noisy present? Or does it have a way to look back and remember what it was doing?
So this brings us to the retrospective side of the architecture. They call it Current-Anchored Intent Retrieval, or KR, because even with DINO features, momentary occlusions, motion blur, or sudden lighting changes can make the immediate present ambiguous. KR lets the model look backward at its recent history to gather stable evidence of its overall goal.
And the mechanics of KR are really interesting. They use a frozen Qwen3VL model. This vision language model processes the current context, what the robot sees right now, plus the language instruction, like pick up the red block.
Right, and it uses that to create what they call semantic anchors.
Yes, semantic anchors. Then they introduce 8 learnable queries. These queries take those semantic anchors and use cross-attention to selectively pull evidence from the recent DINO history. Specifically, they sample frames at 4 distinct temporal points, T-24, T-16, T-8, and T-1.
And by querying those exact historical points, the model distills past actions into short horizon intent tokens. It's a semantic summary of recent task progress. And just like the masking we talked about, these intent tokens are injected only into the action expert.
But I'm looking at this and wondering, if DINO history is inherently so stable, why do we need the complex Qwen3VL anchoring step at all? Why not just pool the DINO history, average it out, and feed it straight to the action expert to save on computation?
Well, the ablation studies, they did explicitly answer that. They tested a variant called naive history retrieval, which is exactly what you just described, unanchored DINO history. And when they ran that, zero-shot performance on LIBERO-Plus dropped to 56.5%.
Oh, wow. That's a huge drop.
Yeah. They also tried keeping the Qwen3VL anchor, but swapping historical DINO features for VAE features. That only hit 64.7%.
Which makes sense. VAE history is just a sequence of pixel changes. And in a visually shifting environment, pixel changes are just noise. You need both to hit the full model's 72.8% success rate.
Exactly. The takeaway is that history without an anchor is overwhelming. If you just dump 24 frames of DINO features into the action expert, it drowns in irrelevant semantic data. The current semantic anchor from Qwen3VL acts as a highly specific filter.
It tells the model what intent it's actually looking for.
Right. It basically says, hey, I'm trying to pick up a red block, but my view is blocked. Look back through the stable DINO history and extract only the features relevant to approaching that red block.
That's fascinating. Okay, so we've built this massive semantic-temporal architecture, dual-space future experts looking forward, current-anchored intent retrieval looking backward, all while dropping the future heads at inference for speed.
Yep.
So what happens when we unleash this on the benchmarks and on actual physical robots?
Well, in simulation, it just dominates. On the standard Libero benchmark, ST-WAM hits a 98.7% success rate. On RoboTwin 2.0, which focuses on highly complex bimanual manipulation using 2 arms at once, it hits 92.8%.
And it's doing this without massive embodied pre-training.
End-to-end, beating models that trained on internet-scale robotics data.
Okay, but simulation is one thing, right? The real test is the physical world, where visual shifts are totally organic and unpredictable. So they deployed ST-WAM on an Agilex Piper 6-Duff single-arm robot.
Right.
They set up 5 complex manipulation tasks: arrange flowers, drawer organization, bean stooping, arrange fruits, and hang mug. And they didn't just test under perfect lab conditions. They introduced severe visual distribution shifts.
Yeah, they really pushed it. They changed backgrounds from matte to reflective surfaces, altered lighting from ambient to harsh directional shadows, even changed the appearance of the target objects.
So what were the numbers?
Under nominal clean conditions, ST-WAM achieves a 79.3% success rate compared to Fast-WAM's 64.7%. That's a really solid improvement right there.
But the critical data point is the compound shift, right? Where they changed the background, the lighting, and the object appearance all at the exact same time.
The ultimate stress test, the Michigan snowstorm for a robotic arm.
Exactly. And under that compound shift, Fast-WAM completely collapsed.
Yeah.
Success rate dropped to 15.3%. It basically lost all ability to function. But SWAM, dealing with the exact same brutal perturbations, held strong at 48.0%.
That is incredible.
Yeah. And when you average the performance across all individual and compound visual shifts, SWAM averages a 61.5% success rate. The Fast-WAM baseline average is just 25.8%.
So it's more than doubling robustness in the real world. That's not incremental. That is a fundamental step function improvement in autonomous systems deployment.
Totally.
And what I love is that the paper actually shows us how the model achieves this. They provide these striking attention heat map visualizations. They mapped exactly where the action tokens were tending in the visual space.
Oh, I love those heat maps. Yeah. When you look at the action to DINO attention, it is laser focused. It sharply highlights the specific manipulated objects and the critical interaction regions, the handle of a drawer, the rim of a mug, the stem of a flower.
But then you look at the action to VAE attention, and it's a mess. The attention is scattered randomly across the whole scene. It's looking at the reflective texture of the table, the shadow on the wall, just empty space next to the object.
It visually proves the whole thesis of the paper. DINO provides the task-focused semantic cues the robot desperately needs, while the VAE is just entirely too distracted by the literal pixels.
It proves we have to stop forcing models to perfectly imagine the literal visual future. Empowering them to focus on the structural, semantic meaning of the world is clearly the paradigm shift we needed for robust world action learning.
Well said. But, before we wrap up, I want to leave you, the listener, with a final provocative thought to chew on, something that pushes beyond the scope of this specific paper.
All right, let's hear it.
So ST-WAM brilliantly solves visual distribution shifts using semantic stability. DINO knows a mug is a mug, even in bad lighting. But what happens when the visual semantics are identical, but the physical properties of the world change?
Oh, interesting.
Yeah, imagine deploying a robotic policy to pick up a mug that looks exactly like a heavy, dense ceramic mug, but it's actually made of ultralight styrofoam. Or deploying policy trained on Earth into a zero-gravity environment on a space station. The pixels are the same. The semantic meaning is the same. But the underlying physics governing the interaction are completely alien.
Right, the dynamics just don't match.
Yeah, exactly. So could we eventually see world action models that don't just rely on visual semantics, but dynamically construct entirely new, on-the-fly latent spaces for unseen physical environments? Could a model use multimodal feedback like tactile sensors in the fingertips detecting slip, or audio sensors hearing the scrape of an object across a table to effectively rewrite its own internal physics engine in real time?
That is, the moment we conquer visual hallucination, physical hallucination definitely becomes the next great frontier.
For sure.
Building a dynamic latent space that can adjust to unseen mass, friction, and gravity on the fly, it will likely require exactly that kind of multimodal sensory integration you're talking about. It's a phenomenal challenge for the field.
And a perfect problem for the community to start tackling.
Yeah.
Thank you for joining us for this technical session of AI Paper Slob. We will catch you next time.